Hello friends, welcome to my channel Easy CE. Today we will discuss a topic that is very useful in digital communication systems, that is sampling theorem and its proof. Let's see whether it is justified or not, this theorem. In that theorem, it is being stated that a signal can be represented in its samples and it can also be recovered back from its sample if and only if the sampling frequency fs is greater than or equal twice of fm, where fm is the maximum frequency present in the message signal, right? So main theorem of the sampling is fs greater than or equal twice fm. So what is the minimum sampling rate it should be if I want to recover back the message signal from the samples? That is twice fm. That is the minimum frequency requirement, and that minimum frequency of the sampling rate, that is fs equals to twice fm, is known as your Nyquist rate. So what is Nyquist rate? That is twice fm, the minimum sampling frequency required to recover back the message signal. Now let's come to its proof. Suppose this is my message signal, a simple sine wave that is represented by xt in time domain. So if I make it a Fourier transform, it will become the frequency domain representation like that. In the frequency domain, it would look like that, where the maximum frequency present is fm. Right now I have taken some signal that is called pulse train, that is train of pulses, all the pulses having amplitude of 1, and this is called train of pulses, and the Fourier transform of this becomes this, and each having an amplitude of 1 at an interval of fs hertz. There is fs in twice fs, 3 fs, 4 fs, and similarly in the negative side. Now if I multiply this train of pulse with this message signal, it would look like this, because these are having an amplitude of 1. So 1 into whatever, it will give the value of this, and in the middle it is 0. So 0 into whatever I am multiplying with this 0, it is become 0. So in the middle it is 0, and 1 into whatever value I have. So this is the sampled signal in the time domain of that sine wave. Now if I represent this sampled signal in the frequency domain, it would look like that. First, from minus fm to plus fm, having a center frequency 0, then fs minus fm to fs plus fm, having a center frequency fs. Similarly, it will have another simple frequency twice fs. In the negative side, it will also continue in the negative towards minus infinity, and it will continue towards the plus infinity. So each having a bandwidth of twice fm and having a center frequency 0, fs plus 2 fs plus 3 fs plus 4 fs, like that. And in the negative side, it is also same. Now coming to the proof. First, there are three cases. First, fs equals to twice of fm. When fs equals to twice fm, you can see I have already said that it will have the center frequency 0, fs, twice fs, like that. So if fs equals to twice fm, so twice fm minus fm is fm, but here 0 plus fm is fm, and again twice fm plus fm is 3 fm, and here twice fs equals to 4 fm, so 4 fm minus fm and plus fm, so 3 fm 5 fm. So wherever the first one ends, the second one starts, whenever the second one ends, third one starts. So you can see there is no overlapping each in occurs there. So from here we can easily say that there is no noise, there is no aliasing effect, so I can recover the message signal very easily. Similarly, in the case 2, if fs is greater than twice fm, so this there was no gap, there will be gap. The more f is greater than the twice fm, the gap will be more, so it will continue looks like that. But in case 3, whenever fs is less than twice fm, whenever it was equal, it had no gap. Whenever it is greater than twice fm, there was gap. Whenever this fs is less than twice fm, there is no gap. Instead, there will be overlapping, because my fs was less than twice fm. Mathematically and graphically, it will overlap. The highest frequency components parts in each band will overlap with each other, and this is called aliasing effect, and the noise will occur. So higher frequency components where the overlap occurs, it cannot be recovered back. So if I cannot recover back, so I should not keep this fs less than twice fm, otherwise I can't recover back the message signal from its samples. So you can see the sampling theorem is proved. So fs should be kept equal to twice fm or greater than twice fm to recover back the message signal from its samples. So that's how very easily you can prove the sampling theorem, and it is very easy, you can see that. So a signal can be represented in its samples, and it can be recovered back from its samples if the sampling frequency fs is greater than or equal to twice fm, where fm is my maximum frequency present in the message signal. So thank you. That's how you can easily prove the sampling theorem. Thank you for listening, and if you like this video, please subscribe to my channel, and we'll back again with some other topic in some other days. Thank you.